I thought about it. I really thought about it, but decided that like if the university tells me I have to have class, maybe I should do it. I mean, like seriously, if I would have just recorded this lecture at home and everybody watched on YouTube, I think we all would have been happier. But oh well. Especially given that today is sampling, and honestly, this is one of those things that for those of us in the bench science world, it's you're probably not going to use this very heavily, if at all. I'm presenting this lecture mainly just from like a statistical literacy point of view as much as anything. I feel like if you've taken elementary statistics, you should at least have some idea about this stuff, but it's not likely to be useful in the bench science world on a regular basis, and you may get like one homework question on it, and after that, I'm never going to torture you with it again. So, quick review of sampling. As you'll recall, that the vast majority of the time we're not going to be able to look at every single member of a population, so we just choose some subset of the population, hope that it's a reasonably representative subset, and then try to draw inferences based on this subset. And to avoid getting a biased sample, the best way to do it is probability sampling or random sampling, where every member of the population has a non-zero probability of being chosen. So now I'm going to discuss several types of random sampling. Again, this is just so you're familiar with the basic issues and terminology, but yeah, that's what I really should have done, just like not taught this lecture at all due to snow, and then we really all would have been happier. But simple random sampling is one form of sampling that's probably the most commonly used form, and basically, as the name implies, it's the very simple approach. You have a population with n observations in it. The probability of drawing any given observation is just 1 over n. In other words, there's an equal probability of selecting any given item in any given item or experimental unit in the population. It's the simplest sampling method and probably the most commonly used. So, simple example of this, say that there are 1,000 patients at your clinic, 20% of them are diabetic, you want to select 100 patients. So you just choose 100 patients at random. The probability of selecting any one person is 100 out of 1,000 or 0.1. And the probability of selecting any given set of 100 people is the probability of selecting any other set. And most likely you would expect to get about 20 diabetics, i.e. 20% of 100, but there's no guarantee of that. You could end up with no diabetics at all. If you got a freaky sample, you could end up with a sample that was entirely diabetics, which is unlikely but possible. Oh, simple random sampling doesn't give you any control over the number of diabetics in your sample. So, advantages and disadvantages of simple random sampling. The advantages, it's simple and it's easy to explain, easy to analyze, and it, generally speaking, minimizes bias, particularly if your population is large and your sample is large. You can show the probability of getting a biased sample decreases as your sample size increases. I mean, even a couple dozen, it's unlikely to be biased. Once you're doing a couple hundred, it's virtually certain that it won't have severe bias. The drawbacks of simple random sampling is you have to actually be able to sample any member of the population, which, particularly if your population is large, that just isn't going to happen. If you're trying to figure out Obama's approval rating or trying to do a presidential election poll, there's simply no way that you can sample from the population of all registered voters in the U.S., or not even registered voters, all the people who are going to vote in the next election. You don't know who's going to vote. Even if you did, some of them won't have phones or won't be reachable. And if you can't sample any member of the population, simple random sample won't work. And another drawback to simple random sampling is that if you want to make inferences about certain subpopulations, you may not get enough of them. For example, let's say you're doing a presidential election poll, or you're trying to figure out Obama's approval rating, whatever the case may be. You do a sample of size 200. If you, in a sample size 200, you could very well end up with maybe only like 5 to 10 African Americans, for instance. That's probably not a sufficient number to draw a decent number of, to draw any sort of reasonable inference about how African American voters as a whole think. So if you just do a simple random sample of the entire population, there may be small subpopulations that you don't have enough data to draw any inferences on. And one way to get around that is to do what's called stratified random sampling, as I'll explain in more detail here in a minute. The stratified random sampling, it's related to the idea of blocking that we discussed on Wednesday. The idea is that you divide your population into strata of groups that are similar in some respect, and then you sample separately within each stratum. And then you basically combine the various strata to get your final results. So the presidential poll example that I just gave, it would be like, say you have a database of white voters, a database of African American voters, a database of Hispanic voters, whatever the case may be. You would basically sample from each database separately to make sure that you have a sufficient number of voters of minorities in your sample to be able to draw some reasonable inferences. So in the example of this clinic, say that you want to be able to draw some inferences about the differences between diabetics and non-diabetics. So you want to make sure that you have a sufficient number of diabetics in your sample. So you just say, rather than just randomly selecting 100 people where everyone has an equal chance of being selected, let's do a simple random sample of 50 diabetics out of 200 and 50 non-diabetics out of 800. That ensures that there will be an equal number of diabetics and non-diabetics in the sample. If you want to compare diabetics to non-diabetics, you have enough data to do so. And so what's the point of this? Well, as I said, it's related to the idea of blocking. That, for starters, well, aside from the blocking consideration, it just makes sure that we have sufficient samples, we have a sufficient sample size in each stratum to draw inferences about each particular stratum. If you want to know about the voting preferences of African Americans, you interview enough African Americans that you can draw some inferences about the population of African American voters as a whole. It also reduces the probability of a biased sample if, when you do your survey, no African Americans pick up the phone and you end up with a sample that's too wide or too affluent or something like that. And another reason to stratify that's unrelated to these other considerations is that it can increase your efficiency. That, again, I won't bore you with all the gory details, but if you have but if your strata are homogeneous, it turns out that you can get a smaller variance with the same sample size if you stratify each group separately than if you just throw them all in the pot and sample from equal probabilities of each. And you can probably just take my word for that because I don't want to bore you with all the math behind it. But the but it turns out for the same sample size, you can get better variance that way. And some more terminology, when you take this sort of approach, you can use the terms oversampling and undersampling, that if the population is 20% diabetic and 80% non-diabetic, then we would expect that then if you didn't do any sort of stratification, you would expect to have 20 diabetics and 80 non-diabetics. So if we instead select 50 diabetics and 50 non-diabetics, and then you would say that we oversampled the diabetics and we undersampled the non-diabetics. And so what's the point of oversampling? Well, if a particular stratum is of a special interest, then you can reduce variability by oversampling from that stratum. For example, if we want to compare diabetics to non-diabetics, if we oversample from the stratum of diabetics, then we can reduce the variability in our inferences about diabetics, which, yeah, I guess I basically said all of that. You can tell I didn't sleep enough last night. And another reason why you may want to oversample is if you know that one particular stratum is more heterogeneous than another stratum. Like, I'm trying to think of a good example of this. Well, I guess we could take politics again. Say that, say for instance that like part of your database of phone numbers is like a list of known NRA members, for instance. For them, you know practically every single one of them is going to vote for Mitt Romney. You don't need to sample that particular group very extensively. On the other hand, say that like you have another database of, I don't know, let's say like middle class voters in Ohio, some notorious swing group like that, who may determine who's actually going to win the election. Well, you want to make sure that you have a very accurate estimate of that particular stratum. You just say, okay, we'll just call a couple people on our NRA list just to make sure that, just to make sure that our numbers haven't shifted too much since the last election, but we'll focus most of our resources on the swing voters who are actually going to determine the election. So if you know that one particular stratum has higher variance than another stratum, then you can reduce your overall variability. That's kind of the intuitive idea behind what I said before, that stratification can be more efficient sometimes. That if you have a couple subsets with very low variability, say NRA members, or I'm trying to think of the other side, like hippies who live in Berkeley or something like that, you don't waste your precious resources sampling from those. You sample from the more heterogeneous groups that are going to be more informative. And a third type of sampling is what's known as multistage sampling, which is typically used in very large studies. It's probably not something that you will ever use if you're just running experiments in your lab. Maybe you might run across it someday if you're ever involved in a huge study like Haynes or something like that. But, like I say, for the sake of statistical literacy, I'll go over it briefly. Multistage sampling, which is otherwise known as cluster sampling, is that basically you divide the target population into groups or clusters, and then you first select a sample of the clusters that you call your primary sampling units, and then once you've selected these clusters, you either take all of the experimental units in a given cluster, or you sample within the cluster to get your secondary sampling units. And if needed, you can iterate this process several times. And the reason to do multi-stage sampling, well, the main reason is because if you're trying to sample from a really large population, you may have no choice. Say you're trying to sample from the entire population of the United States, then you're not going to be able to come up with a list of every single person in the country. And even if you could, trying to randomly sample from that list and contact each one would be ridiculously expensive. So a very large-scale study like that, you really have no choice but to do multi-stage sampling. The disadvantages are several. It's that analyzing the data is trickier. Designing the experiment is uglier. There is a greater risk of bias due to a non-representative sample. And when you go through several layers of clusters and start sampling from a final cluster, you often end up with a somewhat homogeneous group, so that you need larger sample sizes to draw inferences about the entire population. That, again, let's take a presidential election example. Say you divide the country up into counties, then within each county you select a couple towns, then survey people within each town. If you end up with, say, like a rural town in Utah where I grew up, where pretty much everybody is voting for Mitt Romney, again, you end up with a sample that doesn't tell you very much about the entire population. That to do the population level inference, you would have to find a whole bunch of these little towns, and you may end up having a larger sample size than if you just sampled from the overall population. Oh, as I said, an example of when you might want to do multi-stage sampling is the Haynes study. Some of you may have heard of it. It was UNC was involved with it somehow. I don't know the exact details, but it stands for the National Health and Nutrition Examination Survey. That basically they were trying to study various items related to nutrition among basically anyone age 2 or over in the entire country. Obviously, there's no way that you could create a list of everybody in the country, and if you could, contacting those people would cost way too much, so they had to do a multi-stage sampling design. And the way they did that is their primary statistical units, i.e. the first set of clusters, they just created a list of all the counties in the U.S. I mean, it's relatively easy to find a list of every county in the country. And I mean, you could just perform a simple random sample on this list of counties, but they decided it would be better to do a stratified approach that basically they wanted like both rich counties and poor counties. They wanted counties that from various different regions in the U.S. They wanted like majority white counties, majority African American counties, majority Hispanic counties, and so forth. So hence they did this stratified random sampling, and so on. And then within each county, they define these secondary sampling units to be city blocks or areas in a map. So once they had randomly selected these counties, then they selected certain city blocks within the map to be their secondary units. Then within each city block, they came up with a list of households, and then they randomly selected some of these households, and then at the end they select one individual from each household. So yeah, complicated and annoying, but it's the best way to get a reasonably representative sample if you're trying to do a huge study like Anne Haynes from a huge population like that of the entire United States. So this graphic here illustrates these three different types again. Remember, simple random sample is you just basically throw every single member of the population into a box and draw a bunch of names out at random. Everybody has an equal chance of getting selected. A stratified random sample is you stratify based on geographic region, or it could also be on race or income or gender or whatever other variable that might influence the results. And then you sample separately from within each stratum. And as I said, that can hopefully get you a more representative sample, and it can also get you better efficiency if some strata are more heterogeneous than others. And finally, there's multistage sampling, which is where you split your population up into clusters, then you sample a set of clusters, and then you sample within the clusters or something along those lines. The primary advantage of that over the other forms of sampling is it's just less expensive to implement. Oh, another example illustrating these various sampling ideas was this childhood obesity survey that I discussed on Wednesday, that they wanted to evaluate the relationship between weight and health-related quality of life among elementary school children in Australia. They were hoping to draw inferences on all elementary school children in Australia, but didn't have the budget to sample from the entire country. So they sampled from the set of children in primary school in grades 3 through 6 in Victoria, who had previously participated in a study 3 years earlier. Oh, in this particular study, they collected data from 1,569 children, and they were weighed and measured. They also filled out a variety of questionnaires, both the children and their parents, about physical, emotional, and social well-being, and they found that overweight children had negative quality of life. So I'll briefly describe the study design that they used to select the sample. Is that it's sort of, they did both stratification and cluster sampling here. That first of all, they selected 24 primary schools, that, and to select these schools, they created, first of all, they came up with a list of schools and split them into three different groups, either public schools, Catholic schools, or other private schools. And to select the list of schools, rather than giving them all equal probability of being selected, the probability of being selected was proportional to the size of the school. So a very large school had a greater probability of making it into the sample than a smaller school. And once they had selected this list of 24 schools with a representative number of public, Catholic, and private schools, then they randomly selected a class at each year level within each school. So a homeroom class for some specific teacher for grade 4, homeroom of another teacher for grade 5, and so on. And so what's the point of doing this multi-stage design? Well, like I say, the biggest advantage is cost. First of all, selecting a list of schools, then selecting a list of homerooms within each school, it eliminates the need to just come up with a long list of all the students in Victoria. And also, when you administer the survey, it's much easier and much less disruptive if you just come to such and such a teacher's homeroom class, weigh and measure everyone in the room, administer the questionnaire all at once, rather than just randomly pulling kids out of several different classes. And so, what's the point of the stratification? Well, it ensures that all different groups are represented, that you get public schools and Catholic schools and so on. It also ensures that you have enough children from these different groups. Also ensures that you have the grades, grade 3, grade 4, and so on, are selected more or less equally. And it also gives you the option of under or oversampling if you know that a certain grade, a certain class, a certain grade is highly homogeneous, you can undersample and so on. I don't think they actually did that in this study though, because typically that's not something one would know in advance in this type of study. And the drawbacks is it's harder to analyze, and you also probably need a larger sample than if you just did a simple random sample of all the children in these various grades. And potential sources of error in this experimental design is there were 2,300 students that were selected using the sampling approach, and about 1,900 of them completed the survey. I mean, generally speaking, if you get a response rate that high, that's pretty good, and it's not something that you're going to lose a lot of sleep over when you write a paper describing a result. I mean, I think that's approximately the numbers that we have in one big study I'm working on, where we lost about 22% of our people to follow up shortly after the study started. But there's still some potential sources of error here. For example, say that males were less likely to complete the questionnaire than females. And if there are systematic differences in the responses of males and females, that could introduce bias into your study. And this isn't an entirely hypothetical example here. Do you have a question, or were you just stretching?
Yeah, so like if you use, I don't know, 20% of your male population, is it right to like randomly take out 20% of your female population, or is that?
Good question. Yeah, you probably wouldn't want to do that for several reasons. I mean, number one, if you spent the money collecting the data, you hate to just throw it away. That's probably the biggest reason. And number two, that basically makes the assumption that those who don't, there's no systematic differences between those who fill it out and those who don't fill it out, which is a pretty big assumption. That, I mean, because I'm working on two different studies right now where basically we collected some baseline measurements, then tried to collect some follow-up measurements later on, and quite consistently, it's the same groups of people who don't complete their follow-up measurements. It's men are much worse than women, lower education levels are associated with being less likely to fill it out, various things like that. And also, I mean, we were studying effects of psychological distress, and people who were really depressed or anxious were also less likely to fill it out. And in our case, we did some fancy methodology to try to convince ourselves that our results wouldn't have changed too much if these people hadn't flaked out on us. But I mean, the bottom line is you don't know. I mean, if there's some systematic difference between those who fill it out and those who don't fill it out that you can't account for, then you've got bias, and there's really absolutely nothing that you can do about it. Oh, all you can do is just kind of acknowledge in your paper, we lost this many people. Luckily, it's a fairly small number. We don't think it's going to bias our results because, but it could. I mean, the only alternative is just to throw up your hands and give up on the study, which, if you've invested millions of dollars in the study, you don't want to do. But, yeah. So, one way or another, if males were less likely to fill out a questionnaire, that would be an example of non-response error. Or if when you were preparing your list of schools, there were 2 schools you accidentally forgot to include on the list, that would be an example of undercoverage. Oh, a little more terminology on sampling, and this we will actually use a little bit later in the course. When we talk about sampling, there's sampling without replacement and sampling with replacement. And the best way to remember the difference between those two is just like the proverbial balls and urns that people always talk about when they're trying to explain sampling. That, say you have an urn with a bunch of balls in it. If you sample without replacement, that means you reach in there, you take a ball out of the urn, you leave it out, then you take another ball out, and another one out. Every time you take it out, it stays out. You can't select it a second time. In contrast, when you do sampling with replacement, that means you pull a ball out of the urn, make a note of what number of ball it was, then you throw it back in. So you could, in theory, draw the same ball out a second time. And we'll discuss later on in this course at least one case where you would want to do that. But usually when you're designing an experiment, you will virtually always, if not always, want to do sampling without replacement. And that's, in terms of sampling, that's most of what I have to say today. Now just a few more comments on questionnaire design. George Gallup, who founded the Gallup poll, said that selecting and wording questions is really important, that depending on the words you choose, you can get different reactions, or you also have to consider like how hard the question is to understand, how complex it is, how long is the questionnaire, are people going to get bored and stop filling it out, etc., etc. And as I said, like the order of questions can influence responses, and if you put questions at the end of a long survey, that can be, then sometimes people won't pay attention when they fill out the last couple items, and if you put questions that first talk about a problem, then if you ask about how important the problem is, you can get a different response. So again, these issues come up in presidential election surveys, for instance, that good polling design dictates that if you want to design a survey to determine who someone's going to vote for president, you will typically want to put that question at the very beginning of your survey or close to the beginning, because if you put it after you've already asked 25 other questions, by the time you get to that one, people are going to be like, yeah, whatever, just get off the phone and leave me alone, thank you very much, and may not give very much thought to the question. And also, if you ask about a particular problem, or even ask about something related to the problem, then you can get different responses. I mean, sometimes, like, unethical polling firms will take advantage of this. Use a political example again, that say that, oh, for instance, do like a really egregious example. Let's say that you're a polling firm for Mitt Romney and you want to create a poll to make him look good. It's like, ask a question at the beginning. Are you aware that the deficit is increased by this amount under Obama? Are you aware that Obama wants to take away your Social Security, or that he wants to turn us into some sort of communist utopia or whatever? And then say, and who do you want to vote for president? You're going to get a much higher percentage of Mitt Romney than if you just ask at the top, do you prefer Romney or Obama? Similarly, I mean, even if you just do something simple like, are you aware that the size of the federal debt is 16 trillion or whatever? Do you think it's important that we reduce the debt? You'll get a much higher percentage of people who say yes than if you didn't ask that question before it. So, moral of the story is the order of the questions is important when designing a questionnaire. And sometimes people won't give honest answers if it's a sensitive question. And a classic one of that is like, have you ever used illegal drugs? They've done surveys of this with veterans and so forth. A lot of times, if you just ask the question, have you used drugs before, almost all of them will say no, because they're worried that they could lose their veteran benefits if they admitted to that. So they'll do an alternative design where you say, flip a coin. If the coin lands heads, if you've never used illegal drugs, say no, otherwise say yes, something like that. And they do it that way, then suddenly the percentage of people who report using drugs increases noticeably. And another classic example of this is if you ask people how many sexual partners they've had, pretty much every time that survey's ever been conducted, the average number for men is noticeably higher than the number for women, which, if you think about it for a minute, someone is quite obviously not telling the truth here. And so, another way that you can, aside from the flip a coin, sometimes people are more honest if you do it in front of a computer or do some sort of automated telephone interview or something like that. And other design questions to keep in mind: closed-end questions versus open-ended questions. Generally, closed-ended questions are preferred, both from a data analysis and also not having people, in a perspective, not having people get bored from your questions. You also want to keep in mind skip patterns, that if there's questions about menstruation, you put a little note in your questionnaire if you're male, skip these next set of questions. You also want to make it easy to read, easy to fill out, blah, blah, blah. And to give another example of how bad question wording can cause problems, Miller Brewing once did a survey where they surveyed beer drinkers who drank both light and regular beer, and who drink both Miller and Budweiser, and they asked which beer has more taste, Miller Lite or Bud Light, and most people responded that Miller Lite has more taste. Does that prove that Miller Lite tastes better? Well, not necessarily. There were two different problems with the survey. The question wording is, what beer has more taste? Well, if you take one sip of it and you're gagging because the aftertaste is horrible, I mean, you could say that it has more taste. That doesn't mean that it has a good taste. A better way to phrase the question is, which beer do you prefer the taste of? And their sampling frame was also only the people who drank both, and so that excludes the people who only drink Budweiser because they think it tasted better. And in this particular example, supposedly independent third party, the Bud Light was better, was preferred by light beer drinkers, although I'm trying to remember why I put independent in air quotes. I think it actually wasn't independent when I did more research on this, but whatever. The point is that a poorly worded question can give you misleading results, and also a bad sampling frame that if you exclude a certain set of the people who are likely to respond a certain way, you won't get a representative sample. So, things to remember for today is that a simple random sample is the most straightforward approach, and it's probably all you'll ever need to worry about in the bench science world. But there are situations in more complex surveys where you wouldn't want to do it. If you're doing a larger sample with homogeneous subgroups, you may want to stratify. And if you're doing something gigantic, then you may want to do something like multi-stage sampling. And when you design surveys or put together questionnaires, you want to make sure you do a good job of it, or because a poorly worded questionnaire can also bias your results. Any questions about anything today? There was one other announcement that I forgot to make at the beginning. I should probably send an email around given the sparse attendance today. Based on the responses to the doodle poll, I'm tentatively thinking that we'll probably have it Tuesday night, probably around 5:30. Seemed to work for the greatest number of people. But that said, I mean, there really wasn't a good time that worked for everyone. And if you're interested in attending the discussion section regularly and that time is bad for you, let me know. Either send me an email or fill out the poll yourself, and we'll see what we can do.